In mathematics, to solve an equation is to find what values fulfill a condition stated in the form of an equation. When seeking a solution, one or more free variables are designated as unknowns. A solution is an assignment of expressions to the unknown variables that makes the equality in the equation true. In other words, a solution is an expression or a collection of expressions such that, when substituted for the unknowns, the equation becomes an identity. A problem of solving an equation may be numeric or symbolic. Solving an equation numerically means that only numbers represented explicitly as numerals are admitted as solutions. Solving an equation symbolically means that expressions that may contain known variables or possibly also variables not in the original equation are admitted as solutions. For example, the equation x plus y equals 2x1 is solved for the unknown x by the solution x equals y plus 1, because substituting y plus 1 for x in the equation results in plus y equals 2 to 1, a true statement. It is also possible to take the variable y to be the unknown, and then the equation is solved by y equals x1. Or x and y can both be treated as unknowns, and then there are many solutions to the equation. Equals is a symbolic solution. Instantiating a symbolic solution with specific numbers always gives a numerical solution. For example, a equals 0 gives equals and a equals 1 gives equals. Note that the distinction between known variables and unknown variables is made in the statement of the problem, rather than the equation. However, in some areas of mathematics the convention is to reserve some variables as known and others as unknown. When writing polynomials, the coefficients are usually taken to be known and the indeterminates to be unknown, but depending on the problem, all variables may assume either role. Depending on the problem, the task may be to find any solution or all solutions. The set of all solutions is called the solution set. In the example above, the solution equals is also a parametrization of the solution set with the parameter being a. It is also possible that the task is to find a solution among possibly many. That is best in some respect. Problems of that nature are called optimization problems. Solving an optimization problem is generally not referred to as equation solving. A wording such as an equation in x and y or solve for x and y implies that the unknowns are as indicated. In these cases x and y. Overview. In one general case we have a situation such as f equals c, where x1, xn are the unknowns, and c is a constant. Its solutions of the members of the inverse image f minus 1 equals t1 times tn, f equals c, where t1 times tn is the domain of the function f. Note that the set of solutions can be the empty set, a singleton, finite, or infinite. For example, an equation such as 3x plus 2y equals 21z with unknowns x, y and z can be solved by first modifying the equation in some way while keeping it equivalent, such as subtracting 21z from both sides of the equation to obtain 3x plus 2y minus 21z equals 0. In this particular case there is not just one solution to this equation, but an infinite set of solutions which can be written 3x plus 2y minus 21z equals 0. One particular solution is x equals 0, y equals 0, z equals 0. Two other solutions are x equals 3, y equals 6, z equals 1, and x equals 8, y equals 9, z equals 2. In fact, this particular set of solutions describes a plane in three-dimensional space which passes through the 3 points with these coordinates. Solution sets. A solution set is the set of values that satisfy a given set of equations or inequalities. If the solution set is empty, then there are no x's such that the equation f equals c, in which c is a given constant, becomes true. For example, let us examine a classic one-variable case, using the squaring function on the integers, that is, the function f whose domain of the integers defined by f equals x2. Consider the equation f equals 2. Its solution set is the empty set, since 2 is not the square of an integer, so no integer solves this equation. However, note that in attempting to find solutions for this equation, if we modify the function's definition, more specifically, the function's domain, we can find solutions to this equation. So, if we were instead to define that the domain of f consists of the real numbers, the equation above has two solutions, and its solution set is square root 2 minus square root 2. We have already seen that certain solution sets can describe surfaces. For example, in studying elementary mathematics, one knows that the solution set of an equation in the form x plus y equals c with a, b, and c real-valued constants with a and b not both equal to 0 forms a line in the vector space R2. However, it may not always be easier to graphically depict solution sets. For example, the solution set to an equation in the form x plus b plus c z plus dw equals k is a hyperplane.